So thank you very much for Professor Bihas for the invitation, and it's certainly my pleasure to share my research. And good afternoon to everyone. So the topic I'm going to talk about is mobile AI for personalized healthcare. So I will talk about some of our translational research in this topic. In particular, we have been working on some application for skin cancer detection using the mobile AI, and we have been also working on some diabetic wound assessment using mobile AI. So I will talk about this translational research, and then the second half of this talk, I will share some of the challenges that we have faced when working on this application, and also talk about some fundamental AI research that we have done to address some of this challenge. So I think the first half will be more overview, the second half could be a bit more detailed. So I hope that everyone can get something from this talk. My name is Ngai-Man Cheung. I'm Associate Professor with SUTD. So first, I just want to acknowledge my collaborator. I work with Dr. Dong and Professor Tang in the skin cancer project, and also Professor Lee from NUS and SGH on the wound assessment project, and also with Professor Pascal Frasso from EPFL on the mobile AI algorithms. And these are the researchers that have contributed to this work, and we are grateful for the funding from SUTD, MIT, IDC, and Ministry of Defense, NRF, SMART, and also NOH Holdings. So just a quick introduction of my research background. I do research on image and signal processing, computer vision, and AI, and also application of this algorithm to different domains, including the healthcare, transportation, and also the security. So we have publication and patent in this area, and also technology licensing and transfer. And we also have a spin-off company on AI for healthcare. So AI has received some a lot of attention recently. So AI or artificial intelligence commonly refers to the computational technologies that mimic or simulate the human process or the human intelligence process, including the reasoning, adaptation, interaction, and also some sensory understanding, such as image recognition. And in a broader definition, the Cambridge Dictionary describe AI as an interdisciplinary approach to solve some problem of understanding, modeling, and also replicating the intelligence and the cognitive process. So this, so we use ideas from computation and also mathematics, logic, and also biology. So I would like to discuss some example of AI problem that we have been working on. So because my background in computer vision, so then these are some of the computer vision problems that we are working on. I think the most fundamental or important problem is the image recognition. So in this problem, we have a photo of some object, and the task is to identify this object. For example, we have this photo of a soccer ball, and then we try to have the computer system to tell it's a soccer ball. So this is a fundamental problem, and in fact, people have been working on this for 20 or 30 years, because it's actually a very difficult problem. So the difficulty coming from that, the representation of the image that are presented to the computer is actually very low level. I mean, these are just some number in a matrix, and there's a huge semantic gap between the representation and the semantic idea of this photo. So this is a difficult concept. So if I cannot convince you, then first you can try to recognize this image. So this is actually the image that are seen by the computer. So therefore, it's actually not an easy task, because the computer sees this just this number, and then how to actually understand this is a important problem. But it's a fundamental problem, because able to solve the image recognition, then we actually have developed some mechanism to understand the content of the image. Then we can actually move on to some other high-level reasoning task. For example, the object detection is another task that we are given this more complicated picture, and then we try to identify different types of objects in this image. For example, the apple and also the table. So we try to recognize the object, try to detect the object, and also try to localize the object. So another more high level reasoning task is this visual question answering, which is a very hot topic now in our community. So the task is we are given this sentence or this question and also some images, then the computer should try to provide the answer. For example, for this question and also this picture, then we ask where's the child sitting, then in this case would be the fridge. And also say for an image like this, then we ask what's the mustache made of, then we should actually, the computer should be able to provide the answer. So definitely this requires more high-level understanding of the picture or the image content. Okay. And the other also quite exciting task is image generation. So in this case, these are some of the images that are human face that are actually synthesized by the computer. So in this case, this is a system that produces a lot of these synthesized image, and in fact, you can see that some of these are actually quite good looking because I think they use a celebrity face data set, so therefore, if using my face, then the result could be different. Okay, so it's a complicated task because now the computer has to understand what is a human face before it can actually synthesize some of this face. So I want to emphasize that the system is not just remember the face and also doing some interpolation. It's really a creative process that the computer system try to learn about what's a model for a human face and then use it to try to synthesize some of these faces. Okay. So in fact, the second half of the talk, I will actually try to discuss some of the algorithm for this task because it actually create the opportunity to generate some data from the computer, which is very important for this for many of this data-driven approach. Okay. Okay, so definitely there's a lot of excitement in AI in health and medicine. For example, AI is being used in some of the health information system and also some predictive modeling and decision support system, and also some medical image analysis and also diagnosis. So in fact, AI or computer has been used in health and medicine for some time. For example, this is a work in 1972 that is on using the computer and some form of the AI to diagnose the acute abdominal pain. So this is some of the work. But with the recent availability of the data, computation, and also advance of the algorithm, we actually see a lot of excitement in this area for AI in health in medicine. So this is a figure showing the number of publications in this topic, and you can see that there's actually an exponential increase in the number of papers on this topic. And my group has been working on this idea of mobile AI and also to apply to different healthcare problems. So the mobile AI involves a ordinary smartphone and also a sophisticated AI algorithm that is reside on the smartphone to do some edge analytics. So with this AI algorithms, now the smartphone can be a system to analyze the personal data and also to do some predictive modeling. So the smartphone is actually a remarkably accessible device to facilitate collection of a lot of this personal data. And then with the AI engine there, then now we can actually do a lot of analysis and also to develop some more personalized healthcare system. And this is the outline of my talk. And first, I will talk about some of my applications on this idea of mobile AI for personalized healthcare. In particular, I will talk about one skin cancer detection system and also another diabetic wound analysis system. So some of the image in the second part, in this application, could be a bit disturbing, and my apology if some of the picture could be could cause some disturbance. And then in the second half of the talk, I will briefly talk about the challenges that we have faced in some of these applications, and also I will deep dive into some of the fundamental AI research that has some potential to solve some of these problems. Okay, so I will first discuss our skin cancer detection system using the mobile AI. So here our goal is to achieve early detection of the skin cancer. So skin cancer, in particular melanoma, is one of the most deadly forms of skin cancer. It's responsible for 75% of the death due to skin cancer, and because of the potential to spread to other parts of the body. So in spite of the advance in medicine, in fact, the rate of melanoma has been increasing for the last 30 years. So in this year, more than 70,000 people will suffer from melanomas in the United States. So for melanomas or for skin cancer, early detection is really a key to reduce the melanoma mortality. So if we can detect the disease earlier, then we can have a much higher chance and also increase the survival rate. But it's actually not that easy because it will require frequent visits to the dermatologist. And for most people, I mean, especially in the early stage, then you don't feel any discomfort. Then there's actually no motivation for you to arrange to go to the dermatologist. So that's why, although I think many people know that if you can detect the disease, then you can actually have a much higher chance to survive. But still, it's actually not difficult. It's quite difficult to implement. So in our ideas, we try to develop this accessible detection system using the mobile phone and AI. So we see the opportunity that increasingly mobile phones are equipped with multi-core CPU, GPU, and also high-resolution image sensor. So we want to develop a system that the general public can use it for preliminary melanoma self-screening. So our idea is that the general public can use this system to take a photo of the skin mole, and then our system will try to compute the risk score and also make some recommendation. So then the general public can do it in a more frequent base. So why this is possible? Because in fact, for the dermatologists, they also use some of the visual feature to perform the assessment. So therefore, we believe that if we are able to capture the picture, and if the system is intelligent enough compared to the dermatologist, then potentially we can actually do some assessment. For example, the dermatologist will use some of this feature like the asymmetric to indicate to make the decision whether the skin mole is the normal skin mole or is a cancerous. So the other feature could be, say, the border and also the color. So like if your skin mole has multiple colors, then it's actually a high-risk skin mole. So, however, these are actually some of the concepts that are very subjective. So, I mean, even when we are working with the dermatologists, it's actually difficult for them to, I mean, sometimes they can make the decision, make the judgment, but they cannot actually tell us, I mean, how they actually make this judgment. Because I think the intelligent system for human could be actually quite complicated, that it's actually difficult to describe in word, and also, therefore, it's actually not easy to implement into a computer system.
So I think other non-visual, for example, texture of the mole, they would account for characters and form.
Right. I think the texture is also one of the features that they can use. I mean, that's also something that we try to capture in the picture. Because in the picture, then we can do some processing to get the texture information. So I think the visual features we can use in our system, but definitely there's also some other information that might affect the likelihood of skin cancer. If it's beyond the picture, then we will not be able to use it. Okay, so this is a very subjective concept, so it's actually not easy to implement into a computer system. So in our work, we make use of the deep learning or the deep neural networks. So I think the idea is that we try to have some image or data for the skin mole. I mean, they are labeled. I mean, they are being labeled as normal and the cancerous. And then we have the algorithm to automatically discover some feature that could be useful for this task. So therefore, this is a data-driven approach because we actually give the data to the system, and then we try to use the algorithm and in particular the deep learning to try to extract the useful feature for this task. However, there's still some problem because the neighbor data set by the clinical expert is actually quite limited in size. I think this actually perhaps a quite common problem in many of the healthcare situation. That because in this case, the image has to be determined by some clinical procedure in order to have the gold label. So, for example, we require some histopathological analysis to confirm whether it's a normal skin mole or is a cancerous skin mole. So, therefore, we do have only a limited number of images that we can work with. So, it might not be sufficient for using some of the deep learning and the deep neural network. So, in this work, we perform a so-called the transfer learning idea that we use a convolutional neural network. It's a specific types of deep neural network that has basically used the convolution to extract the features at different layers in order to come up with the inference. So and then we use a pre-trained one. So the pre-trained one is based on the natural image because we don't have a lot of this skin mole image. So we instead use the natural image to train the network, but we transfer the system and then just do a fine tuning for our application. So so therefore, this is an idea to deal with the problem with the data, and but there's also some uncertainty that because now the network is actually being trained on a data set of common objects, so it could be quite different from the skin mole that is the target of this application.
How many layers do you train on your actual data? How
many
of the top layers do you train on your data?
Right, that's a good question. So I think we fine-tune only the last 3 layers, and then and then the top 5 layers we just use this as it is from the pre-trained network. Right. So because the last 3 layers is more application dependent, and then the first 5 layers is more generic feature extraction.
And how did you know that you should use 3 and not the last layer, the last 2? How do you know this?
Right.
How do you know how many of the layers are going to be transferable? How many of the layers?
Right. Yeah. So I think somehow it's actually a not easy question to answer because I think it's not easy to tell which layer. Because different layers capture the concept at different level. So we might not know which layers could have the important information that we can transfer. But there's a framework called the coarse validation. I think maybe most of you are also familiar that we use a data set that is the validation data set, and then we use it to basically try to set up some of these hyperparameters of our system, and then we actually try to use this validation data set to assess the performance, which layer we should use to transfer to the system.
So do you take a model, for example, where there's only 3 layers, then 2 layers, and compare the performance, or you keep your full model and then have randomly selected?
Right.
So what do you do? I don't know that part.
Definitely. Yeah. That's actually a fair question to ask. I think the alternative would be you just have a small network and then you try to train. So in this case, indeed, this is a system that can perform better because there's also some low-level features that are common between the natural image and also the skin mole image. And I think we take advantage of another large data set to learn these low-level features, but now we actually just put in some new concept, in this case, the skin cancer detection.
Is it to work? Because I'm not familiar, I'm not a computer scientist.
Right.
With deep learning,
right.
How do you measure how deep it has to be?
Right, how deep it is. Right.
How deep? Like 5 layers, 6 layers, 7 layers?
Right, so each of these would be 1 layer. 1 layer means that's a layer to do the convolution and produce an iteration. So in the architecture, in fact, there's a well-defined architecture to tell you how many layers is your system. Right. But I think deciding the number of layers is also one of the hyperparameters that people have used. Right. Right. The image dimension, the input dimension.
C1, C2.
Right. Right. So I think for this part, it's also using the validation data set. There has been some work on try different image size and use it for use a validation data set to determine what would be the good size for this problem. Right.
And it's a small number, but they are 18, 40, 56. So each
right.
You have like number.
You mean?
384.
Okay. So this actually the number of free feature map. So because for each layer, we actually perform filtering using many different filters. So for each filter, we will produce one feature map. So in this case, in fact, for the last layer, we use 384 filters in order to produce this result. So therefore, we have a 3D free feature volume that correspond to, the depth basically correspond to the number of filters we have used in the last layer.
So that varies, right?
That varies. That's also a design and hyperparameters. I think many of these, to some extent, there's some theory on this, but there's also a bit of empirical and also validation to design some of these hyperparameters.
So one more question is that, I understand the prediction part. What about the model interpretability? Can you interpret the model?
Right, that's actually one of the points that I want to mention. It's actually not easy. Although there has been some work on understanding how the deep neural network make a decision, but I think most of the work are still, there's still progress to make to understand the interpretability of the result. And this is actually one of the criticism that people always talking about these types of technique. The system might be able to produce some decision, but it's not able to tell what's the theory, what's the mechanism to produce this decision.
And for standard perceptual model, there is a connection between the non-parametric statistical model
right.
and the standard two-dimensional model. Has there been work on training this in non-parametric statistics? Probably not, right?
Right. I think because first of all, the system is actually substantially much larger than the other types. So it becomes more difficult to perform some of this analysis. Okay. Okay, so we have this system, and the challenge here is that the data set pre-trained for this network could be a bit distant from the image that we are doing for the task. Okay, and on the other hand, I think the result is also quite encouraging. So although I think if we can adjust this problem between the two different data sets, then we can further improve the performance. So for example, so this is the work that we have done, this is the study that we have done about 2 years ago. So we are using the deep neural network features. That means that we are using our proposed system using the deep neural network, and then we compare with the other previous work. So I think in terms of the sensitivity, in terms of the specificity, I think these are all very encouraging and outperform previous work. So for this work, we have the technology license to a company, and then currently it's undergoing regulation and also some deployment in Australia. So we'll see whether, in fact, the technology can bring an impact to the practice. Okay, so this is one of the applications we are working on using the mobile AI for skin cancer detection. So the second application is the diabetic and chronic wound analysis. Okay, so some of the image could be a bit disturbing, and my apology for that. Okay, so chronic wound is actually a major healthcare problem. So say in Singapore, there's more than 600,000 diabetes, and more than 28% of them will develop the chronic wounds. So chronic wounds are the wounds that they will take several months or year to heal. And if during the process, if the wound is not properly managed, then this might actually lead to some complication like the amputation or some other complications. So it's an important problem because so for the homebound patients that require home care, in fact, more than half of them suffer from chronic wound. So on the other hand, the current practice for chronic wound assessment is actually quite primitive. So it's mostly based on visual inspection. That means that the healthcare workers actually have to travel all the way to the patient home and to examine some of these wounds. So they have to do this frequently because they have to understand the progress of the wound. And then for each wound, usually they spend about half an hour to do all this measurement and assessment. So it's a very labor-intensive process, and also because of the limited number of home care workers, so therefore, in fact, a lot of them are quite overloaded. And this also caused some problem like the delayed assessment and also some delayed treatment. So our idea is to use the mobile AI to develop a system that can, is a smartphone-based system that can be used easily for the healthcare worker or also from the home family helper to try to perform this wound assessment. So in particular, we try to develop a system that can, the wound care worker can take a picture of the wound, and then our system will do the assessment automatically. So this includes the measurement of the size of the wound and also the location of the wound. And the other aspect would be the tissue analysis, because there's several different types of tissue on the wound, and different tissue actually means different progress or different condition of the wounds. So the other is early infection detection. So we make use of the visible light, and we also make use of the thermal imaging to try to get more information about the wound. And then we use this thermal image and also the visible light to try to pass that into our AI system in order to determine the condition of the wound. So, so there's also some complication that we also make use of, and also the blood circulation. We can actually get some of this information from the thermal image and then use it and pass into our AI system to determine the condition of the wound. So there are 7 different types of wound tissue, and like the healthy granulation and also the hypergranulation. So these different types of tissue are, identify different types of tissue are important because it actually give you information about the condition of the wound, whether the wound is getting better or is getting worse. However, some of the wound tissue actually can be quite difficult to distinguish. For example, the hypergranulation and the healthy granulation. They means different condition of the wound, but even for a human or for some junior wound nurses, they also have difficulty to distinguish different types of tissue. So for this problem, we use a deep neural network to accomplish this. And again, it's a design that is similar to the skin cancer case. But in this case, what we are doing is a patch-based classification. That means that instead of taking the whole image and do the analysis, now we actually look at just one patch of the pixel. One patch of the image, and then to classify this into different types of tissue. So the reason is that because in a typical wound, there could be several different types of tissue. So in this case, we have the healthy granulation. We also have the scarf here. So then we actually have to identify what are the different types of tissue in this single wound. So we have this patch-based approach, and then we pass through the convolutional layers and then the fully connected layer. And then at the end, we perform some dimensional reduction before we pass into a classification system to decide what's the tissue type of this patch. So if we go through for the whole image, then we'll have this result to indicate what are the different types of tissue in this wound, and also to estimate what are the percentage of tissue that indicate is the wound is making good progress or the wound is getting worse. So, so this is the work. We have finished one study last year, and again the results are quite encouraging. So, so the first row is our result. I think we achieved an overall accuracy at about 86%, and it's actually much better than some of the previous work. So the research is ongoing, and we are also working on translating this into practice. So in particular, one of the postdocs has taken this and formed a startup company for this work, and he has been working with some of the hospital for the POV to understand how this can be used in the hospital. And they have also performed some comparison with the human judgment, and I think the result is actually quite positive. And in fact, for this work, Professor Bihas has been helping us with the biostatistic consulting. So I think there's some good results even at the in the hospital, and then we're also showing this to some of the ministry, and hopefully this can be actually some work that eventually this could be some real impact to the clinical practice.
So on the slide before this, no, the slide before that, so you said dimensionality. So you have all these, you did all this, and then you did dimensionality reduction.
Right. So we take this 1,000 dimension activation, and then we reduce the dimension.
How did you do the dimension? What did you do?
I think we just perform PCA.
PCA. Oh, I
right.
see. So you looked at the major directions.
Right. Major direction.
And you used those in the classifier.
Yes. Yes. I think the idea is to reduce the complexity of this classifier.
This picture looks like an SVM, right? This picture of the classification looks like an SVM picture, no?
This is a SVM.
SVM, right?
SVM, yes. This is a SVM classifier.
So PCA in the dimension reduction.
PCA is this part. Sorry, yes. So PCA is this part, and then after we perform the dimension reduction, we pass into the SVM classifier.
And you mentioned that all these are edge analytics, so everything is done on the phone?
Yes, yes. So we actually have some work. Unfortunately, I will not be able to cover in this talk, but we have also worked on some work to try to reduce the complexity of the deep neural network so that we can put this on the phone without compromising the accuracy.
So before doing PCA, do you use any kernel to project it, or you don't do a kernel projection?
No. I think we.
Simple linear.
I think yes. Okay, so this is the first half of my talk, and then the second half would be basically I want to briefly mention some of the challenges that we have faced, and then I will want to deep dive into one of the fundamental research that we are doing that might potentially address some of the challenges that we have. So I think in terms of challenge, the first problem we have is the prediction accuracy. So because for a computer algorithm, it's difficult to achieve 100% accuracy. So we always have this question of, what would be a sufficient accuracy for this particular application? For example, for the skin cancer case, perhaps if we miss one cancerous sample, it could have actually quite significant impact to the user. So that's actually one of the problems with some of these computation algorithms. So while you can actually have some trade-off between the sensitivity, that you can actually try to keep improving your sensitivity, but at the end, if you get a lot of this false positive, it's also not a very good system to use. So this is one of the issues. And also the input data could be also quite noisy and capture a lot of measurement error. So we have to actually deal with some of this error in noise when we are doing this, when we are working on this system. So the other problem is the large intra-class variation. So say for the infected wound tissue, in fact there's actually many different types of infected wound tissue. So somehow the system have to able to recognize all these belonging to the same class. It's also not a easy problem. So in addition to that, in fact, there's also some other factors that might affect the clinical outcomes. For example, for the wound healing case, it could actually depend on some other factors. Like, for example, the environment, or maybe the personal hygiene, the hygiene of the person. So these are actually some of the factors that might not have been captured in our model. So therefore, based on only the image, then it could be in some aspect, in some sense, it could be not able to capture all the factors that might affect the healing of the wound. So the other problem would be, as that gentleman mentioned, is the lack of interpretation of the decision. So the AI system what they are doing is actually try to detect some complex pattern in the large data set. So perhaps some correlation, and then use this correlation to perform the prediction. But the system is not able to provide more deep theoretical and also the causal understanding of the data, which might be important for many of the users to understand the decision result. So as a result, in fact, many people criticize this as a black box system, that the system is able to return some outcome, but people will not be able to understand how the system make this decision. So that's also one of the problems that has hindered the acceptancy of the system. So the other problem is the difficulty in data collection. So many of these medical image data sets are quite small. So that also affects some of the state-of-the-art approach that require the data-driven approach. And the other problem is the lack of positive examples. So like in the skin cancer case, it's actually very uncommon to able to get the cancerous sample. So therefore, the positive samples are especially more difficult to obtain. So the other problem is to annotate some of this data. In fact, we require a clinical expert to provide the label. And this is also a very time-consuming process and also a very costly process. In particular, in some of the cases, some clinical procedure like the histopathological analysis might be required in order to obtain the gold label for us to build a training data set. Later on, we use it to train our system. So all these data are very costly and time-consuming to obtain. So this is actually one of the problems that we have faced when developing some of this application. So on the other hand, a good quality data is actually very important. I think some people say it's good data, you can actually create a good model and then garbage in, garbage out. So therefore, we have to deal with this problem. So there's several approaches to deal with the problem of difficulty in collecting the data. So here I would actually like to discuss one of the approaches that has a lot of attention recently. I might not be able to cover all of this, but I hope I can still give you an overview of this approach. So this is called the generative model. So basically, it's a branch of unsupervised training techniques that people have used. So as the name suggests, I think basically how we try to train a model to generate the data. Okay, so these are actually some of the outcomes that we have done. So here the setup is that we have a system. The input to the system is just some random noise and some random vector, and the output is actually some of these images. Okay, so specifically we want to have a training data, and then we want to compute a model that eventually this model can produce the image that captures some of the characteristics of this training data. So that's the goal of this generative model. So of course, addressing the data problem is an important goal because it can actually solve many of these practical problems we have. But potentially, the generative model can also capture the deep understanding of the data and also the essence of the data. And this is actually very useful for some of the complicated reasoning tasks. So the introduction here is come from a famous quote from Richard Feynman that what I cannot create, then I do not understand. So therefore, if the generative model is able to synthesize some image, then potentially this generative model can capture the deep understanding of the data, and then we will be able to use this model to enable some more difficult reasoning tasks. So that's actually one of the reasons that why people are so interested in this generative model. And of course, solving the data problem is also very important. Okay, so I'll go back to the difficulty in collecting the data. So one might actually wonder whether, in fact, the synthesized image have enough quality that we can actually use it to improve our system. So the generative model, in fact, has improved quite a lot in the recent years, and we have started to see some encouraging results in this for this problem. For example, this is a recent work by a team in Israel, and in this case, they are dealing with the lesion classification problem that they try to use the generative model to synthesize some image, and then these synthesized images are being augmented into the training dataset to train the classifier. So the result is actually quite encouraging. Some of these synthetic image looks quite similar to the real image, and in terms of the performance of the classifier, they also are able to obtain quite remarkably improvement in the system, say from sensitivity from 78% increase to 85% by augmenting this synthesized image in the training dataset. And also the specificity has also quite some improvement. So to some extent, we are seeing some of these encouraging results, although later on I will discuss that there's still a lot of problem in this generative model that we try to address.
So are they using probabilistic models to form their generative? Is the generative model a probabilistic model? So is it a stochastic model? Does it involve stochasticity or deterministic?
But it is a, later on, in fact, I will discuss more details in one of these generative models. So we sample the input from a random noise or random vector, but after that, there's a deterministic step to actually produce the vector, right? Yeah. So later on, I will discuss some principle of these generative models. Okay.
And you're saying though that by training, you're saying that it should be possible if you combine the synthetic data with your real data.
Right.
You can improve your classifier.
Right. So I think we are starting to see some of this result of improvement. I think several years ago we are still not able to do this because the synthesized image quality is not that good. It actually makes the classifier worse than before. But I think because there's really many people working on this, and there's quite some improvement in the generative model. So I think we started to see some more encouraging results, but we'll actually see whether this could be actually ultimately can be one solution to this. Okay. So in fact, I want to point out that for medical image, in fact, it might be actually for medical image, it actually might be easier for this idea to work because the medical image, if we're looking at a more specific problem, the variation of the content is actually could be less than some of the actual image that we have. So for a actual image, it could be different types of objects, and then we have to, the generative model have to learn all these different types of model. But for a given medical problem, maybe in this case there's only a few different classes, then the generative model will try to learn these few different classes. So therefore, in fact, the potential to apply this idea for medical image could be, or I would say more high chance to success than the general problem. Okay, so now I want to talk about the some of the state of the art in this generative model. So one of the work is this so-called the GAN or the generative adversarial net. Okay, so this a work that proposed in 2014. So the idea is that we have two systems, both of them are neural network, and then they try to contest with each other in this system in a zero-sum game. Okay, so in particular for the generator, it takes the random noise and then it goes through this neural network to produce the fake image. So this is one part of the system, this is the generator. And then on the other hand, we also have another deep neural network as a discriminator. So this discriminator tries to classify the input is the fake image from the generator or it is the real image from the training data set. So, and then it will produce a score, and the higher the score, the more the discriminator think that the input is a real image. So that's the mechanism. So to some extent, you can see that these two systems try to contest with each other, try to compete with each other, and then during this process, both of them will be able to improve the quality. So the trick here is that we use backpropagation to backpropagate the feedback from the discriminator to the generator, so that the generator will be able to update the parameters to improve the image quality based on whatever the discriminator has made the decision. Okay.
So, can I ask you?
Sorry.
Are you going to tell us how you update the weights in the generator on the next slide?
I will give a bit more details. Okay. So basically, the training process. After this, if there's some question, feel free to ask. Basically, the training process is captured in this min-max two-player game with the value function v. So here is the d is the discriminator score. So this is the score output from the discriminator. So the higher the d, the more the discriminator thinks that the input is a real image. Okay, and then here the c is the normal is the random noise or the latent code that pass into this generator. So therefore, GC is the fake image. Okay, so now how to make sense of this equation? So from the discriminator point of view, the goal is to maximize this log dx, because if x is a real data, then the training should be try to maximize the score for this real input image. Okay, so therefore we try to maximize this, and furthermore we want to also maximize this equation for the discriminator. Also try to maximize this log 1 minus this GC, because this means that if the input is a fake image, then the discriminator should be small. Okay, so that's the training of the discriminator. We want the discriminator to be able to identify that if it's a real image, we have a high value for the d, and then if it's a fake image, we have a small value. Okay, so that's the part for the discriminator. But for the generator, on the other hand, it has a opposite purpose. So the the generator try to minimize this term. So to minimize this 1 minus DGC, or it actually try to maximize the DGC. That means that given a fake image, then the generator try to learn to maximize the discriminator score. So thereby it can actually confuse the discriminator. So that's the competition game between the discriminator and the generator. Okay, that is captured by this equation. Okay, so first I also try to talk about this slide. This slide basically, or this figure try to illustrate the training process for this GAN system. So here the D is the discriminator score. So D is the score that we use to classify whether it's real or fake. So the higher the score, then the more the discriminator think that the input is a real image. So here is the data distribution. So it's the distribution of the training data, which the goal of the training is to have the generator to capture this distribution. So here we have the domain of C. So this is the random noise, and then G here the generator is this mapping the random code to the data sample. Okay, so in this case, because the generator map all this random sample into this small interval, so therefore we have more synthesized sample in this interval, and therefore the distribution induced by this generator is given by this one. Okay, so the green one is the distribution of the generator capture. Based on this behavior. Okay, so so when we update the discriminator, so now the discriminator score become better. So basically, the discriminator score is determined from the probability distribution, because here in this interval, the probability of the real data is higher than the probability of the synthesized data. So therefore, the discriminator, if the discriminator is being trained properly, then it should actually return a higher score for this interval. Okay, as we have seen in here. And also the opposite would be in this region, because the probability of the synthesized data is higher than the real data. So therefore, in this case, the discriminator score should be small for this part, because the discriminator try to think that these are the fixed sample, okay, over this interval. Okay, so this is the update of the discriminator. On the other hand, the generator, it basically tried to use the gradient of the discriminator to try to improve the score. In particular, in this case, you can see that the generator, after the training, it tried to shift the sample from here to this interval. The idea is that it tried to use the discriminator score to try to improve to update the generator, because the goal of the generator is to maximize the score for this for the DGC. It tries to maximize the discriminator score. So therefore, it will look at the gradient of the discriminator and try to improve itself. So as a result, you can actually see that there's a shift in the probability distribution induced by this generator. So the distribution try to eventually shift to the real data distribution. So if everything goes well, then at the end of the training, we'll see this situation that the real data and the synthesized data have the same distribution. So because the generator is smart enough to look at the gradient and try to shift the sample that it tries to synthesize. So at the end, then the generator distribution and the data distribution would be the same. And at that case, then the synthesized sample and the real sample would be difficult to distinguish. And the discriminator will always output the same score. It's 0.5, because everywhere here, then it has the same probability of data distribution and the synthesized data distribution, and it becomes difficult to distinguish between that. Okay. So later on, if there's some question, I could actually also discuss at the end of this talk, because I think this is actually a bit detail about the training process, but indeed it actually gives a lot of insight how this setup can actually generate a good sample. Okay. I think I might not have enough time to discuss other details. Okay. So but it's actually a very ideal case. The one I show is a very ideal case, and then I have just one. Right.
Sorry, first.
We're getting way too interested.
Sure.
Right.
So are you missing some of the positives that might be the very big
The green curve. In the first one, right. In fact, this is right, exactly. So it's actually in the initial stage of the training. So that actually means that the green curve is the probability distribution of the generator. So this actually means that the generator is producing a lot of sample that does not look good. Okay, because it's actually the probability of this interval is high, so therefore it's producing a lot of sample that does not correspond to the training data. So in this case, in fact, you can imagine that the generator is actually producing many of these garbage image that look different from the training data set. Right?
So my understanding seems to be that in order to have a good generator according to this criteria,
right.
Not only want the generator to produce samples that are like the training set, but also you want the generator to output distribution that are
exactly.
the same as the training set.
Exactly. Right, that's actually the ultimate goal. If we can achieve that, then now when we do the random sampling, then we always get the data that correspond to the same statistic of the training data. So that's the ultimate goal. Okay. Thank you for pointing out.
The reason for wanting this kind of generator is because after you get the generator,
right. So then you can produce a lot of this sample. So like in the skin cancer case, if I am able to use this generator to capture the data distribution, then now I can just take this generator to produce a lot of these images.
Right. So I guess you need a new deck. You train on the one data set like this, suppose I had 2 sets of skin images. I would do this on one set, and then I would then use this to augment the data on my other
yes, right. Or the other usage, like in this paper, I mean, what they have done is they use some, they are starting with a very small data set. I mean, it's a small data set. I mean, not even able to train this generative model, but they do some simple augmentation. Like they rotate the image, they flip the image. So these are some simple augmentation that you can do to the data set to train this generator. So after you train the generator, then now you have a system that can create a more diverse sample for you to train the classifier. So that's how people try to achieve the problem.
This is very interesting. What I was thinking was that with the skin cancer case, my basic understanding is that clinicians actually can tell quite well what is quite dangerous. But could you feed into it ones where they're uncertain, but you knew the outcome was actually cancerous? So you have a generator which adds value to the clinician's uncertainty. Does that make sense? So in case maybe you're creating something which, how are you making sure you don't create something that doesn't tell them something they already don't know?
Definitely. It's a very fair question. I mean, in fact, the quality of this synthesized data, I mean, that's always the question. I mean, whether the quality of this synthesized data, in fact, can improve the data set to train a better classifier. So, again, we are seeing some encouraging results because the generator has been improved quite a lot. I mean, using some of this approach and also some other technique. So we are seeing some encouraging results, but I will be also quite cautious about this technique when you apply to some of these applications. Whether in this particular application, then the synthesized sample have the good quality that you can actually augment your data set to improve the classifier rather than to reduce the accuracy.
To me also this is a very interesting idea. So, and I'm just wondering, you cannot just purely randomly generate the first generator. You need something to generate the close, not too far from the real data, right? What do you have to have when you generate the initial generator?
So the initial generator. So Right. So in some of the experiments, in fact, we're actually starting with just random parameters. We start with some random parameters to try to build up this distribution. Right. I think if we easier in that case. I mean, in some case, we also, for a more complicated problem, we also use a pre-trained network that understands some of this image feature. But in some of the cases, in fact, we're actually starting from scratch with a random parameter and use this mechanism. This is the maybe the baseline, maybe the basic framework. But actually, after this, there's a lot of research to improve this framework because it's actually not a easy problem. If you just do that, then it's actually not easy to converge. Then since then, there's actually a lot of research, and including some of our work to try to improve the convergency of this system. Okay. So then first, I just briefly mentioned. This is the ideal case because we have just 1D data. It's just 1D, but imagine that when we have an image, this is actually a very high dimensional space. And then also this distribution has only one mode, but in real application we have multiple modes, and it's a very complicated probability distribution. So therefore, no wonder that there's still actually a lot of problem to improve these types of approach. So one of the problems that we are facing, I think we're still facing this problem, is this mode collapse. That means that at the end, in fact, the generator are only able to produce the sample that are very similar to each other. So it get the diversity that we would actually hope for from this system. So in this case, it's a 2D latent space, and then we try to use the generator to produce a digit. But in this case, you can see that most of the latent space, in fact, produce a single digit 1. Okay, so this is not good because we actually want the system to produce a very diverse data set. Okay, so if we go back to the setting, then it actually means that for the real data distribution, now we have 3 different modes, but the generated data has only able to capture only 2 modes. So the generator is not able to produce the sample related to this mode. So this is actually not good. I mean, in fact, this is actually the result of one of the recent systems, and then it's still a problem that people try to solve. Okay. So the other problem is this gradient vanishing. So this problem occurs because when we have a perfect discriminator, in fact, it's actually not difficult to train a perfect discriminator because it's easier to criticizing rather than to produce the result. So therefore, it's actually not difficult to train a perfect discriminator. In this case, the perfect discriminator would be one that, so the blue color is the real data and the green data is the synthesized data. And then now actually the discriminator is doing very well. I mean, it can actually identify that these are the real data, so therefore I get a score of 1. And that is the fake data, so therefore I get a score of 0. But the problem is that now there's no discriminator gradient to allow the generator to improve. Because eventually we actually want to get a good generator, right? But because all these sample, the discriminator produce the same score, which is 0. So therefore, there's no gradient for the discriminator to follow in order to improve the system. So this is also a problem. So that means that now the generator is being get stuck here. I mean, it does not know which direction to move in order to improve the quality of the generator. Okay. So
this is a case where the generator is just gone off and produced data that's totally different.
Right.
And because it's so totally different, you don't get any kind of slope, any gradient.
Exactly.
To move back.
Exactly. So in the previous case, I mean, when I draw this, then hopefully there will still some overlapping. Then you have this gradient to guide the generator to improve the configuration. So the generator can actually take this gradient to move to the direction where it can actually improve the quality of the synthesized sample. But in many of the cases, like if we're starting with the random generator, then usually we actually have this situation. I mean, the generator has a very bad result, and then it's easy for the discriminator because the discriminator can say it's the good result, it's the bad result, and then it actually make a perfect decision, but it does not provide the gradient to improve the generator. So therefore, I mean, it might sound a bit strange, but sometimes we actually want to slow down the convergency of the discriminator in order for the generator to learn something. Okay. So I think I will not be able to describe our own improvement, but basically we have made some contribution to improve the training of the GAN so that we can address some of the problem, the gradient vanishing and also the mode collapse, right? But I think we are. I mean, if there's some interest, I mean, we can also discuss offline. Okay, so I think these are some of the results and some of the images that we have generated. So that's a score called FID. So it's a score basically it compares the feature from the real data and the synthesized data. So it's sort of some distance between the features, and then the smaller the distance, the better is the system, and then we are able to achieve a quite encouraging result compared to some of the state of the art. Okay, so then first I should conclude the talk. So I've discussed some application of mobile AI for personalized healthcare, including the skin cancer detection and also the the cognitive wound assessment. And there's some challenges we have faced, and I also discussed one approach to solve the problem in getting collecting the data. So basically, we have proposed two techniques to improve the gain so that we can converge the gain better and also produce a high quality sample. So I think a final remark would be, we have seen a lot of excitement about the AI, but we are still yet to see some real impact to the clinical practice. I think there's still some improvement in the algorithm, improvement in the system, and hopefully at some point we'll actually see some real impact to the clinical practice. Okay, and thank you very much.
I want to ask a question about the GAN.
Okay,
so,
right.
I'm trying to understand where the okay. So you described how you train a generator so that you can get more pseudo samples, which improves your improves the training of
yes.
classifier.
Yes. Yes.
I'm trying to understand where does the additional information come from? Since you're starting with the actual sample.
Sure,
you're
right.
generating a sample essentially based on the
Sure. That's a fair question. So
you have to use multiple data sets. You
right.
have to use multiple. The final classifier building, that's a different data set from the data set used to train the generator.
Right. So in fact, we use the same data set. I think the idea is that given the training data, the generator is trying to capture the essence of this training data so that it can create more diversity of the data. So that means that when you are given a data set, some of these are training image, then the generator is trying to understand what's the essence in this training data. So if I can understand this, then I can actually now create more different sample. So the essence here is the probability distribution here. So given this data, we try to estimate what's the probability distribution that is behind this training data. If the system is smart enough to capture this distribution, then in principle we can actually produce more data that have the same characteristic.
But I thought you weren't reusing the training set. Like there's one training set that's used to do GAN, and then there's the other training set that's used to do the final classification. Am I correct? Do you reuse are you using your data over again? Training it once for the GAN and then again to do the classification?
We in fact use the same data, also train the classifier. But when we do the testing, when we do the testing, of course we actually use a different data set. But when we do the testing, we have a separate data set, and then it has nothing overlap with the training stage. But during the training stage, in fact, we use the same data first to augment this to train this generative model. So now we have this generative model, then we're able to synthesize more data to augment our data set to train this classifier. So I think, again, to answer your question, I think it's actually the research challenge, whether you can actually capture the essence in this training data so that now you are able to use this to create a more diversity of the data.
To rephrase what you just said, to capture the essence, my understanding from a statistical point of view is that you're imposing a model on how the training set is generated.
Right.
And that model brings you this additional information.
Yes.
That's the insight, right?
Yes. So therefore, I think in fact it's being captured also in this diagram. So eventually, you want your generator to be able to, that's the ideal case that capture the model behind the data. So if you can actually capture this, then now you can just sample from this distribution to synthesize more data.
Kinds of noise to that model in the other augmented version.
In other augmented,
model, you keep the same model, but
we keep the same model.
Other draw from the error distribution.
Yes, exactly. So we can now do random sampling from this model to create a diverse sample. I think to clarify, indeed, when we are doing the testing, we are actually using very different data sets. We don't overlap. So that's the important protocol.
On your final slide, you said that late stage research would be looking at people.
Right.
I was wondering if you could let us learn how that could be happening. Would it be
Right. So you mean impact, right? So that's so I think that that's a complicated process. Right? I mean, I think in our experience we have developed this wound assessment, and then the people have taken this as a startup company, and then there's a phase to adopting this technology to the hospital, and then now there's many complicated factors, whether it's cost effective, and then whether it's in fact able to integrate it into the ecosystem or etc. So I think that's a very complicated process. And for the regulatory approval, in fact, because I mean, like some of the example we have, we actually put this as a class of, I mean, we are not, I mean, we put this, it's not making the diagnosis, but it's providing additional information. So we are actually able to go into the easier class when we are working in Singapore. So, I mean, I think there's a class 1, class 2, and I think we are actually able to avoid the class that are actually targeting for the diagnosis or etc. So that would be a class that is difficult to get through. But we actually put this, or the startup put this as a system to provide additional information. Then it will be actually easier to go through the HSA. Right? But I think that's all these complicated issues that in order to, right. Right, but of course, I think, yes. I think there's still more work to do to be done, and we actually hope to.
I think in the interest of time, we stop here.
Okay. Yes. Thank you very much.